as a homework for you, is I asked you to do the homework on the array. Did you do it? So the array, let's say we have the array that I want to delete some numbers. Let's say I have number 2 here, the 8 here, and the 6 here, number 2 again, number 2 again, and number 0, and number 6 here, let's say. So my homework, the homework I asked you to do is to do this one. Try to remove or delete on instant of a given value from the array. Okay. So I asked you to remove it. So do you have any idea how to do it? Can you share with us? Did you try it at home and homework, everyone? Say yes.
I did.
Yeah, great. Try to tell me what is your solution. What is your solution?
Do I demo the code or?
Maybe let's start by tell us like what is your strategy, what is your algorithms, how you do it, and we'll see the code later.
Okay, so firstly, I will have the steps that I would search that if the specific element that we want to delete exists in the array. And so if it does, we will create a new empty array with the length that is cut by 1, because we removed that specific element there. And so after we found the element in the array, we will iterate the array again to in the array, and the iteration goes like in the array. If the specified element we found there, we will skip it, and we will assign the values from the array to the new one to create a new array.
And finally,
we return the array that the element is removed.
Okay. Yeah, thank you, Ken. Yeah, that is everyone. Can you get the idea? His idea is, let's say in the array I want to remove 2 from the array. What he did is he make a new array. Okay, and actually he tried to reduce the size of the array, but it's not a big it's not a problem there. What do is we say he tried to do is every time we see the number in the array, if it's equal to the given in input, so he skip it. Okay, it is 2, he skip it. 8, okay, he copy it here. It's 6, copy it here. Then 2 skip, and then 0 there, and then 6. Okay. Yeah, this is one way to do. Okay. Of course, yeah, it's good. Yeah, somehow. The thing, there's 2 things I want to clarify here. First of all, that you see that instead of working on the existing array, what we can do is we use an extra memory. It means we create a new array. As this, what we should do is have the same size as a given array. Okay, and then we will copy the value to a new array. That's it. That is a good way. And you see that this guy of thing, we can do the deletion just in one iteration through all element of the given array. It means the complexity is on. Okay, but the we use extra space. Okay, that is the thing. Another thing that just as a warning for Khang and everyone else, think about this situation. The user gives you one input array, and then you work with another array. Okay. In some situation, that is a problem. Let's say, assume that we are all in this meeting. Let's say, online meeting, and then I want to remove all of the annoying guy or hacker or some uninvited attendee in the class. The way that Khang do is, you see, he create a new meeting, no? And he move all the valid user of the meeting to the new meeting. Is it the same, Khang? No? And you see, that is a problem. Because we are in this meeting and we don't want to move everyone to the new meeting and restart. The same there. This, of course, is a way to remove on number 2. But the way you do is we try to move everyone to the new room. Okay? Be careful with that. Because in some time, we want to keep everyone in the existing array. I want just to remove annoying guys from this array. Okay, of course we have many other ways to do, but the solution of Khang is one of them. Thank you, Khang. Everyone, do you get the message there? Hello, is it clear, everyone? You see the problem? So the thing is, we can do that. Of course, we have another solution. Let's say this one, we use an extra array, but not just to store the new data, but we may just to mark the index of the things here. We mark up 2 is in the slot number 0, number 2, number 3, number 4, number 3, number 4, and that's it. And next time we will try to shift it back to the left correspondingly. Okay, of course it takes a bit more time. And to fix the thing that we have with the copy into an array, that we can always erase everything here and copy it back. Of course, it takes us another route. It could be 2n. Okay. So anyway, that is the thing that we normally in this course we just analyze the complexity of an algorithm in time. Okay, but you should aware that people can always improve the performance, the running time, reduce the complexities of an algorithm by using extra storage. That is the way people do. Okay. Yeah, I hope that you get it. Now we back with this one. We have array. We have very basic array. We have basic data structure. For all languages, we will support have it as the native data structure. And then you see that we have some very basic operation in array that will have us to say to like have you to remind or practice on basic like a programming skill with if, else, while loop, and for loop, and we can have us to think about the complexity of the algorithms. Okay, and in that complexities, I now just want to have a quick review. Can you tell me which kind, like name some algorithms on any kind of data structure that you may know that have an operation, have an algorithms that can have O1 as the complexity. O1 is mean the constant time. Give me some more example on that. What kind of operation that we have O1? Hello. What hash map is a name of a data structure. We want to have operation algorithm. Access the element in array. Yes, they very basic but important. Thank you. Means we can access any element in the array if you give us an index. Okay, say. Okay, very good. Any others? Because the one that we have, insert an item to the last position of the array. Okay. Yeah. Okay. Then you can see later. Okay. But think about that, because if we can find something that is O1 as the complexity for algorithms, that is a perfect solution. Okay. That is very good. Okay, so we have array, and then after one-dimensional array, we have like a two-dimensional array. And if you work with data science, we have multiple dimensional arrays. And this one is, they say, two-dimensional arrays, very like a common and widely used data structure for many game or many kind of problems. And if you want to practice more, as you want to play with different exercise and practice your programming skill, two-dimensional array is one of a good topic. Means that, let's say, try to perform some operation like sort of them line by line, sort of them in increasing order from the top to the top left to the bottom right corner. Put it in diagonal, or sort it vertically or horizontally, make it a spiral. This all of cutting with two-dimensional array is a very good place for you to practice if you really say you need to play more with the algorithms. So try to think about this different context like that and just implement the code. Okay. And then you may want to analyze the complexity of your algorithms. Then we have it. Then we move to some other things that we have in linear searching techniques. Means that in this kind of thing, we would try to delete something, we try to insert it into the right position. All of them requires to make a for loop to search through the array. And this linear searching means that if we have to find something, what we can do is just go through all elements in the array to search. Okay. Of course, in the worst case, that complexity will be ON for sure, because we have to go through all of them. Let's say the element is not in the array. Okay. And now there's one thing that people say, if we have order array, it's been sorted array, people can optimize or can have better algorithms for the searching. Okay, that what people name it is binary searching techniques. Do you know about that? Just tell me, like, if you know it. Yeah, great. Okay, great. So now let's try to say play a small game to test your to know a bit more on the binary searching techniques. Yeah, of course. Now let's try, say, binary searching techniques. Now we have guess a number. I have a number for you. And just my information is that will be from 1 to 100. Okay, please guess something, and I try to tell you the result. everyone. Yeah, they play together. 50. I will say 50 is bigger than my number. Okay. So 25. 25. Yeah, of course. Yeah, my question is at the beginning. Yeah, some of you make a guess in some some random starting point. We try to see what is your your argument, why you start at this number. Okay, so let's tell me, like, we can guess anything like that. Okay, but now I would try to answer one of you, like 25 is smaller than my number. So what we can know from that? 25 is smaller than my number. Then my number is in that range. Yep. So that is the very important information. And then try to guess. Take 37. It is still smaller than my number. Yeah, smaller than my number. Okay. Yeah, it's 42 is still smaller than my number. Okay. 43 is still smaller than my number. 45 is still smaller than my number. 47 is bigger than my number. Yeah, that would be 46. Okay, and you will see that, of course, you can guess it randomly. For 46, you can get it randomly, but now we think about the performance, everyone. Okay, so the performance. What is the performance of this? Let's say if what very important here is that if you guess number 50, and I say that 50 is bigger than my number, what you can conclude is this one. This is very important for you. Because of what? Because after you get my feedback, you can ignore half of the range of the input that you have to check. If I say 50 is bigger than my number, there is no reason why should you guess 70, 60, 90, because we know that if my number is smaller than 50, there's no way that my number can be 90. Okay, that is very important information. Okay, and of course, the way people do is the binary structuring. It try to, let's say, in a given range like this one, it try to check in the middle. This is the thing. Let's check the one in the middle and compare whether or not my number is bigger or smaller than the one in the middle. If they say the first, I say no, it's smaller than 50. What you say, you can ignore everything above or equal to 50. That is great thing. And then you have the remaining. In order to repeat the same kind of properties, we break it into the middle. No, 25. I say 25 is bigger, is smaller than my number. I would say this, and you know, as the result is that my number is in this range. Is from 26 to 49. That's it. There's no way that my number is 0 or 2 or 3. We don't need to care about this thing smaller than or equal to 25. That is the idea. So you see that it's very important that every time we make a guess, we can ignore half of the range. That is very big number. If we have million of elements, you can remove half of them. That way, you see, 500,000. That's a lot of number. It means it saves you a lot of guess. If you have to take one by one, just like linear check. Linear check, we just go one by one, step by step. But now we can jump, remove half of the range. That is the binary searching algorithms. And you see, by continuing like this, after like 5 guesses, you can finally reach the number. Okay, that is the binary searching. Just to show you the power of this thing. So we see that every time we make a guess, we can reduce, we can ignore half of the range. Means that is the thing people say that help us to analyze and know that the complexity of that operation is log 2 of n. It means a number of division by 2 finally until you reach number 1. And if you get 10, you divide by 2 as much 4 times, and you will get 1 at the final. So see that if we have a range of 10 numbers, what you have to guess at max, at most, is 4 times. If 100 is 7 times, and you see the value 1,000 times 1,000 elements, just 10 of them. And now think about 1 billion. I don't know if you have 1 billion Vietnam dong in your pocket or not, but think about that. But if I had to guess the exact number, that I know that I may guess that you don't have 1 billion Vietnam dong in your pocket, but I can guess the exact number, exact amount of money that you have by asking you at most 30 questions. You see, that is a big deal. Okay, because you know, you save a lot of time without binary searching. If we had to check one by one, take me say 1 million times for Vietnam dong, because we know that is yeah, let's say 1 billion dong, 1 billion times. So now guess maximum 30 times over 1 billion number. That is a very impressive performance. Okay, do you agree? Let's say you want to check something. I give you a folder of 10,000 students at IU. I want you to find a given person there. If you do it manually in paper, and if you just go one by one, it take you a week. Okay, just 1 second. Sorry, I get. Okay, I'm sorry. Yeah, you see, then of course, then this is one. You see that what kind of properties that we can have here is that we have something that in order, means that with the feedback of the user, we can remove half of the range. That is very important key thing. Okay, now as you can see now, here's the binary searching algorithms. I will show you the code next, but there is the idea. We map it to our array. You see that we have here the lower bound. Okay, the upper bound is mean the range that we try to find the numbers. And what we do always, we check the one in the middle. Okay, and then we compare whether or not the value in the middle is the searching number. If yes, we good luck and we stop there. Very easy. Otherwise, we compare the value of the one in the middle with the given number. Of course, if the number, let's say my number is 20 and the one in the middle is 10, what we can conclude is that 10 here is smaller than 20. Okay, and means that if we are in this one in the increasing order array, everything on the left side of the middle are smaller than 10, and my searching number is 20. This means that no way that my number will be in this part. We can safely remove things. So people will move the range that we need to check by moving the upper bound to this position. Have a look. This one, we skip the number in the middle because we know this number is not the one that we want to find. Okay, and then we repeat that step again by putting it in checking the middle again and just update the upper bound and lower bound again and again until we finally have the result. Okay, so for everyone, if you are not really comfortable with this one, do you have any question, any concern, anything that you want to ask? We're happy to answer. Otherwise, if you don't have question, so everyone please, you know, we are learning, so yeah, that is the thing. So this algorithm, let's say for a moment we assume that our input array is in sorted order. That is our assumption. We can only do it that way, otherwise we cannot apply by researching for sure. Okay, because what can help us to safely remove everything on one side. That is the assumption, the requirement for these algorithms. Okay, now what I want you to do, let's say I have a range of value. I would put it like this one, give it, take it in the chat box. Okay, let's say we have some numbers 1, 2, 3, 4, 5, 6, 7, 8. Okay, now I want you to check for the number 20 at 22 and the number, let's say I will put it, okay, there is 2 input. Try now, your task, try to run the algorithms, okay, and show me step by step after each update of your system. Show me the value of the lower bound. Let's say to start, lower bound is 0, the upper bound is 7. The current, the one in the middle, I will divide by 2 and I get 84. Okay, that is this. And tell me like step by step, say, well, this the first step, and step number 2 is you update lower bound to this one, to update upper bound to this number or something. So everyone just do it. Okay, run the algorithms, this algorithm in the screen, one by one, step by step, with the input for 22 and another is for 119. 19, yes. Okay. Okay, like the message when you finish, and after that we can show your result. Let's show your result in the chat box, like when I tell you. Okay. So everyone try to do it. Okay, thank you, Thành. Okay, take you some time to run it. I hope that it helps you to understand the algorithm better. Now, the others, if you finish, please like the message. You know, I strongly recommend you to have some reaction so that we can, at least I can follow your progress. Okay, so please do the reaction, please. So we have 50 of you here, only 5 of you can finish. Hello, the others. Now, should I now I just so, and one of you please send me put it in a chat box message. your output, please. Thank you. What is it? Yeah. Okay. So at the beginning we have what? Okay. Can you summarize it somehow? So we have what? We have 4 at the current and the beginning, and then we have we update the upper bound, that will become 3. It's been after first step, so we update the upper bound to be 3, so our range we check is 0 to 3. Okay, next time we have 0 plus 3, we divide by 2, we have 2, and we update the lower bound to become 2, and the current name plus 1 is 3. Okay, next time 3, we have exactly what we got. Okay, then what we do next for the others, okay, I cannot see it. For the second time, that we update the low bound first to become 5, and then okay, then update to become low bound again to 7, and update the upper bound finally to 6, and finally what we get is the upper bound is smaller than the low bound. Okay, in this step, so what we have is the upper bound smaller than the low bound. What does it mean by that? It means that we have 2 numbers, one from the left, another from the right. Okay, we try to move them into different direction, opposite direction. Okay, what happened is that if this one cross the others, means that we have went through all of the elements in the array. Okay, so if then we say that we cannot find any numbers in the array that is equal to the given value, so we can stop. Okay, that's good. Thank you. So everyone else, do you have the same result? Okay, so that is the algorithms. Okay, now, yes, great. Now the first question is that you see that I'm working on this algorithm, have us to work on this array, it is increasing our order. Okay, increasing order. Okay, now if I want you to work to run the binary searching algorithms on the decreasing order array, let's say 180, 50, 40, 20, 2, 0. If I have a decreasing order array, is it possible to run the binary searching algorithm? My first question, is it possible to run the algorithm? Yes. Okay, but then can we use this algorithm to run it? Okay. And do you think that we can use these algorithms in the screen to run it? Of course, no. Why? Because there is very different. Let's say last time, why do we have a number? Let's say at here we have 50. Okay. If I have a number to check, my number is 80, what you can conclude is that everything from the left hand side, in the left hand side of 50 can be ignored, can safely ignore this one. Okay. But then if we have this one exactly the same, what we have is 50 there. If we have 80 as the number we want to check, and 80 is bigger than 50, what we do? We should remove the opposite direction. It means everything on the right, because that would be everything smaller than 50 there. Okay, so now your task, tell me how to update the algorithm in order to have us in order to run it for decreasing order array. So update, modify. Okay. This one, I try to make some. Let's say we have an if. So 1, 2, 3. Okay. So where should we modify? And other students, yeah, line number 3. Yes, but what should we do? Yeah, in 3, what can we do? 2 and 3. Okay. And tell me what you want to do. Other students, please try to interact, try to be active in class now, so that I can know you better. Okay. Thịnh suggests that we swap this one, no? We move this one to this, and we swap the position. No? Okay. Yep. This is one way, Thịnh. Great. Everyone else, do you agree? Means if it's smaller, last time we update the lower bound, now we should update the upper bound. Otherwise, yeah, we update the opposites. Thank you, Thịnh. Another solution, we can always do it like this one. Low bound, yes, low bound is the index. Yeah, here it's just the index. It's not a real number in the array, because it will have us to move around. No? Yeah. Is it okay, Minh? Got it? This one, this is almost the same. You can check either case, but no, Khoa. If you check low bound is smaller than upper bound, that is always true. No, normally we start the low bound is here. The low bound is not the number. It's not a value in the array. This is the index. Let's say in my case, let's say we have 100 here. You see, this one is a This is the index. Okay, 80, 50, 20, 10. Okay, so it starts with 0 here and the index 1, 2, 3, and 4. You see, this kind of thing. This kind of thing is a technique that people will use. We have a variable that keep track with the index. It means the object that we are working on. Okay, we are not working with the real number, but just the index. Okay. 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 Any other question, everyone? Is it clear? Hello? The others, is it clear for you?
Yes, teacher.
Great. You know, again, I strongly recommend you to interact to tell me. Okay. Yeah. Thank you. Yep. First, we want to modify it. Now, what we can summarize from this one is that for an order array, it means if we in order, what is good for us is that we have a good searching time. The complexity can be reduced because we can use binary searching algorithms. Okay, the insertion is not good because we cannot put number randomly, like put it in the last position, because we have to put it in the right correct position. Okay, to find the position and put it there. Deletion is not good anyway, because anytime we have to shift it back. Okay, as you remember, in the array, there is the way we organize. For any kind of deletion, we always have to shift it back. Okay, there is no way that we can avoid that kind of thing. Okay, in array. So what we want as a conclusion is, mean next time when you have some problem at hand, if you want to organize your data structure, let's say, then we want to put it to use order array if we want to do a lot of searching. Okay, and the insertion and deletion is not so frequent. Okay, so we save time, we get better performance for our program in general. Okay, so there is an advantage of order array. Okay. Now what we can do is we have this one, the log again, so very powerful one. Okay, just one more thing on this one. Now my question for you is that if we want to if we have an unordered array, it's mean array in don't have any exact don't have any order among elements, and if we want to check for something, can we use binary searching? The first question. If our array is not ordered, it means let's say this is the value of the element. It could be 0 here, is 10, it is 2, it is 20, it is 3, you know. If put it in some random orders, we don't know. Of course, we cannot use binary searching because our assumption on like where should I ignore? Can I safely ignore everything from the left or from the right Of course, no. We cannot apply binary searching for another array because we have no information that can help us to ignore others items in the array. Okay, and then if I had to check an element in there, should I sort the order, sort the array, and then apply the binary searching? Should I sort it first and then run the binary searching algorithm? It depends on the number of input. What do you mean? Now we are considering whether or not we should do something. Okay. If the number is small, just look at one by one. If it's big, what happened? If you have thousands of elements or millions of elements, what should I do? Should I sort them? You say sorting first. Okay, if you say sorting first and then get the run the binary searching. Okay, now can you tell me what is your expectation of doing that? You want to do the sort and then you want to do the check. Sort first, okay, then check. What is your argument, or what is your expectation when you suggest me to do that? Why don't I just check? You say one shot, one sorting, and then check. But what you want? But what you want from there? You want to save for later check. Okay. The goal is you want to improve the performance, no? You want to save, you want to improve the performance. But actually, the question here is, you say that sort will save you 10. You have to think. The question should be asking, like, what is the complexities of the sorting algorithms? No. The question should be, what is the complexity of the sorting algorithm? No. But unfortunately, most of the sorting algorithms is, oh, can you guess? Oh, the sorting algorithm, the n square. Sorting is very complex, everyone, in general. The sorting algorithm is very complex. So normally, if you want to check for something, of course, if it's sorted, you have the binary searching. But if not, you better do the linear check, because finally, if you do the sort, the complexity is on square plus n, log n, log 2 of n. And if you do linear check, that will just n. See? So you save for later, okay? It means like later you should have a lot of searching. Okay, so that is the things. See, of course for binary searching, so we have it. The message here is that sometimes people can say prepare for the features operation, of course, but we should analyze our problem at hand to check whether or not the check in general are more frequent than insertion and deletion. Okay, if in some situation we don't need to check that frequent, just like to store it, put it there, we don't need to solve. If we just store, we don't care, we don't have any need, any case, or rarely we try to find something, so we don't need to solve. If we have to check or get item out of that box, out of that array frequently, so we have to solve. Of course, what we can do is we can prepare for it. It means we don't need to solve it at a bit from the existing data, but every time we do the insertion or in the deletion, we try to keep it sorted in the correct order. Okay, so anyway, you see, that is the thing. Means that we have to check the complexity of all the operation we need to do. Okay, is it clear, everyone? Is it clear? Yeah, it means for the current application, for a situation, I have another array I want to check just for one item. You better run in linear searching. Okay. Yeah. What we can link from this one is just in real life, people normally try to find the best way to do. Let's say you have a messy bookshelf or messy room. I mean, I hope that you don't have that kind of thing, but usually you have a lot of things, a lot of stuff. You don't have it in the like you don't arrange it frequently, so it is not sorted in some order. Then your mother wants you to find something in your room, no? Or if you want to find something in your room, is it normal that you spend time to arrange everything in your room before you try to find your items? Normally, no. If you are in a messy room already or messy bookshelf, you just directly jump into the linear searching. Try to find the item because what you need at hand. You will not spend time to sort them, to arrange them, to find the object. That is the thing. Yeah, of course. Your mother will say, yeah, now let's sit down, take some time to rearrange your room, and then next time you can find it faster. Of course. Okay. And what is the cost? What is the cost in real life? Because next time when you have something that you want to put it in, when you put it in the in your room, you have to find the correct position to put it there. But normally when you have something to put in your room, you just throw it that corner and that's it. No? So the way that we say insertion and deletion, delete and remove and check. People, yeah, I don't know. Sometimes people refer to put it. It means that is like if you put it in order array, you have to. It gives you a good like this one. What do we say? Where's my pointer? What do you see here? We have good searching time for sure, but the time to insert and to delete is not good. Okay. Okay, everyone, that's it for the first part. Okay, I hope that you now see the things. Let's take 15 to 20 minutes if you want to have a lunch. Okay, and see you there. Okay. Okay, everyone. Enjoy Yeah, of course, Kang, the index is just one example of how people can make things easier for the user to say to know what to do and convert it back to a bit easier problem, means how to remove it. Or of course, what people can do with index is we know exactly where we should remove things, and we can compute with complication in the formula to know how many items, how many positions have to shift these number to the left or to the right. Of course, either way, the message there is just to show you that people can use extra space in order to speed up things, like the way that you copy it out to another array and you copy it back. Okay, this is always the case. It's always like that. Okay. So everyone, please like to tell me that you are here. Huh? Yeah, we have 50 of you here. Great. Okay. Thank you. Welcome back. So now try to move on. So you see that now we now move to another usage of array. Of course, it's people use it widely, so we have many use cases. Of course, we can use it for objects in object-oriented programming for sure. We can have a list of collection of students. It's been a list of students. I can search student by name. I want to search insert a student. Put it in the correct position in the array. Okay. My first question is, can we use the linear searching algorithms for the searching to find a student in an array? Is it possible? Linear search? Of course. Yes. There's no difference, no? The one thing that is different is that every time we do, like let's say a list, let's say I have my array list of array of students. Okay. Of course, what I can do is I can always do array of student at index 10. What we get out from that assessing is that we get back one student object, and we can always compare like this one 10 dot GBA, is it bigger than 10 than 50 or 80 or not? We can always do like this, no? We can always check, we can do checks. Just the difference is the way that we access to the data. Okay. Yeah, so we can do the check. Next question, can we apply the binary check for student, array of student? Yes or no? Yeah, if I arrange them. Okay. Yes, of course. If I want to do the body check using like a GBA or some whatever you want, we can always do it. So you see, storing objects has no difference. Okay, we can always perform all of the operation that we have with current array. Okay, and now we have some other thing like we measure on algorithms efficiencies using big O notion. Okay, now just do some wrap up. So we have three kind of basic, I would say basic complexity in time. Of course, we can have the same for in space. Okay, constant means we don't care how many we don't care about the size of the input data. We can always perform the requested operation in a constant number of steps. Okay, we can have it proportional to n. Okay, proportional to log n. You see, we can say log n. We don't care about log 2 of n because we can say if n is big enough, log 2 of n equal log the vector of n are almost the same. Okay, we can just simplify things. Okay, and we have constant time. So we have insert. We have last time I asked you like access the data, like read the data at the given position in array is always constant time. Okay, we can say yeah. On another data structure, we can have like a pick a given value from the stack that we O1. Okay, ON or on many things we have ON, and people can say, well, linear check in on average the number of operations we have to do is n divided by 2 or something. But for complexity, we say we take the worst case scenarios and we say that it will be n. Okay. Okay. And we have binary check in the log 2 of n, and they say if n is big enough, we say the difference is log n. Okay. Now here is the figure that I want to share with you. Is that you see if something is here is the number of elements, here number of steps that we have to perform in order to perform to do the request. If it's O1, it is the perfect solution. Okay, it's been constant time. So if you can do something like that, that is amazing. Then log n, you see, is very good already. Okay. Normally we have log n, on is proportional to a number of elements. We can like 2n, 3n, n plus 100 something. Let's say on, and we put like this. And log, on square can go exponentially that way. But you know that there's many algorithms that go something like power n 2 power n. Okay, and there's something else that is this one, a bigger one. So the complexity of the algorithm could be anything, especially if you know a bit on machine learning and AI. You see that the number of steps, the number of operations that we have to do in order to train a given model is huge. So we have to go through the data set many times. We have to randomly pick them. We have to train it many times. So that is machine learning. So the complexity of algorithm is machine learning is very hard normally. Okay. Okay. So you see that is the thing. And to summarize, we have array, we have another array that is good for instruction. Of course, it's not good for searching, deletion. So we have binary search, good for we can only apply it for order array. Okay. You have bit notion, and if you say the algorithm is 1 or 1 is the best algorithm ever. So we have log n is good, is fair, and this one pretty bad. Of course, in reality, we have very complicated algorithms. Okay, that is. So that's it for array and complexities and things. And I hope that you get some new things on top of that. So now time for question. Do you have any question, any concern, any suggestion to do? My suggestion last time, like at the beginning, I say, if you're not really comfortable with some operation in your array, I strongly suggest you to find or to play with the two-dimensional array, like sorting, searching, make it special form, arrange it as a Sudoku format or whatever. Okay, check whether or not each 3x3 square in 3x3 3x3 things is the sum of them is 9 or something. We can always play with hey, there's someone that I know somehow unmute me. So okay. So okay, so if you want to play with the basic algorithms, so please work with 2D array. Okay, any other question, please? Any question? No? Okay. Otherwise, let's move to the another topics for chapter 2. Of course, I think that you notice that I upload most of the slides to Blackboard. If you want to review or you want to prepare for a section, you can always use it. Okay. And I strongly recommend you to read the book. Okay. That would be better. Okay. So this one. Now we move to this one, is that we try to work with the sorting algorithms. So people say, well, that you may know some sorting algorithms, okay, but now we try to review it. Just tell me, give me some name of the sorting algorithm you may aware of. You know, give me some name of the sorting algorithms. Yeah, great. Purple sort, great. You know, big sort, you know everything? Yeah, great. Purple sort, great. Of course. So it's a good starting point. Now we do again like array. It's quite basic. Now we go through some basic sorting algorithm. The ideas of this part will be, we try to show you algorithms, and I want to show you some analysis on top of the algorithms, and that is the way to have you to analyze all the algorithm in the future. Okay, and and we'll show you some code. Okay. Now, so understand and know how to use the basic sorting method. So we will throw 3 basic sorting algorithms: purpose sort, selection sort, and insertion sort. Okay. We compare their performance. That's it. Okay. So we have this crafting. Okay. First, why we need to sort data? Of course, say you want to use binary searching. Okay, one way, one goal. Otherwise, we can have us to access the data, to query the data better. Say get the lowest price, get the highest most crowded country in O1. You see? Now imagine if you want to find the max and the min value in the array. Is an order. The complexity will be O n. We have to go through all the elements and find the max. Okay. And now if we want to get it in O1, means yeah, we organize our data structure so that people can find the lowest price easier. Each time you go to Tiki, Lazada, you find the cheapest value. Yeah, they sort them already. You just show you the value. That's it. Okay. So you prepare the data, you put it in the sorted order so that we can perform all the operations better. Say a 1. Okay. Oh, yep. So, and many things, if you put it in order, it's easier. And prepare for searching. Okay. So now, we should aware, as I gave you an example before, sorting is time-consuming task. It's not easy. It's not always easy. Okay. So people spend quite a lot of time on imagine how to sort the data better. We have a lot of them, but in this first part, in this thing, we just go through the basic algorithm first, and for the following sections, we try to see different sorting algorithms in detail. Okay. Simple sorting. Remark and zero is slow. Okay, but it's easy to understand. Okay, but last thing, be aware that the performance of these sample sorting algorithms are excellent in some situations. Say if we have small size, it's been very small array, so apply basic sorting algorithms is just enough. Okay, we don't need fancy things. Okay. And all of them, the complexity is O(n) square. Okay. My question for you is that if I have all of the basic sorting algorithms, the O(n) square, should I select an algorithm to run, or all of them are equally in terms of complexity, so we can pick any of them? Say here we have a list of 3 basic sorting algorithms, all of them are n square. Are they the same? And we should not care about that. Just run it. One of them is enough. Is okay. Is it true? Yeah, say the one that is easier to code. Okay. The others? How do you think about that? Fortunately, unfortunately, is it not true? Is it not true, everyone? Because of what? Because no. Yeah, we use existing library in another story. But now, yeah, the thing is ON square, that is the worst case scenarios. Okay, we can estimate that, well, they're almost the same, but for the real performance, we have something that is better than the other. Okay, because the complexity again is in the worst case scenarios. Okay. Okay, so even though they are the same complexity, but depend on the say scenarios, depend on the context, but in general the performance of all of these are of sorting algorithm are different. Okay, in the worst case they are the same somehow, but in general they are different in running time. Okay, so this still we still need to check. Okay, in this case it's sorting algorithm in general, in sorting algorithm, but in general they have many different algorithms for different problem at hand. You cannot say, well, all of them have the same complexity, we don't care. But normally if you want really to optimize, you don't have any choice. You don't have any algorithm that have better complexity, but we can always select the best algorithm among the algorithms that have the same sorting, same complexity. Okay. Method is complexity is the worst case scenarios. The real performance will be different. Okay. Yeah, Phúc, you want to say something? Hello, Phúc. Go ahead, Phúc. Hello. Hello, Phúc, Phúc. Hoàng Phúc. What say? Okay. Tell me when you are ready while you raise your hand like that. Okay. Now. Yeah, say something. Go ahead, tell me. Run pattern, wrong pattern. Oh, okay. Okay. Okay, it's good. Okay, okay. Now, so if you have to arrange players in order to in increasing height, so if you know something on purple socks or some others, so can you tell me the sequence, the way to do, how we do it? Now I have a list like this. I want to arrange them. What should I ask them? What should I do first? Any algorithms? What should I do? First two, then the first two person, no? Okay, and then what? Okay. So say we do this one, and let's say we want them to be in the increasing order, no? So we say we swap them. Okay, we move this guy to this position, and this guy to this position. Okay, and then next. we continue this one, and then okay, and then swap if needed. You can compare and swap if needed. Okay. Now there is one algorithm. So we have the basic sorting algorithm, and as you can see there, the key operations that we have in any sorting algorithm will be compare and swap. Okay, so we compare and then we swap or we copy. That is the very basic step. Okay, yeah, and the thing is, that is another thing that people may need to check. They don't need additional space. In some situation, that is important. Okay, do you agree? Say, I have one student, one class, one room of 100 students. Okay, and we want to sort them. Of course, one way to do is I can ask for another room and move everyone one by one, just like the way that you delete the item in the duplication array, the array with duplication. So we will ask for another room just to put things there. Okay, it could be like that. But if the size of the input is big, we don't want to require an extra space. Let's say in your hard drive, you have your hard drive almost full or just half full. You just want to sort your file in increasing order. Of course, they don't need extra space. If they need extra space, it means you cannot sort the data if you use more than half of the size of your hard drive. See, don't need additional space is quite important in some situations. So remember about that. Okay. Now we try to show you the purpose of, if you don't know it yet, but if you know it, we'll try to give you some special remark on that. The basic idea, we compare, as your friends say, compare the elements there, and then if it is bigger, then we swap and then just move it again and again. Now I just want to show you some up. No, I don't want to stop. Well, they stop. Just 1 second. Where's my slide? Something wrong? Okay, sorry. Now, just want to show you the purple shocks in action. Okay, just look at it first, and then we will see some other thing. Okay, so now people try to show us different sorting or different scenarios. Let's say, see, can you see it? There is the purpose of that. Run randomly, and you see that they call it purple because they try to bring the item, the smallest item, to the top. You see, try to bring it to the top. Okay, and here is some different scenarios. Say they resulted, reverse order. See? And pre-randomized means with duplication. Okay. So you see that for this reason people call it bubble sort, because it try like in a bubble in your bottle of water. When you inverse them, they will put it in the in the move it to the top. But now my back to this one. Here is a way. So you say we pick the two first item and then we compare. If this one is smaller, we move it here. We move this guy to this position, okay, and this guy to this position. We swap them. So if we have, and then we continue to compare the next two items. This one. Okay, so it's actually this guy. Now let's try to put it as the in numbers. I just want you to play a bit with that one, so that if you okay, it's just okay. Here is an example. So everyone just this one run, just run it manually. Write out, run the algorithm manually on your own on a piece of paper, just to practice the idea. I will do it like for the first one for you. This one, I will say this one, I compare this one and this second. So it is smaller. If it's increasing order, I will put 78 here and we put 89 here. Okay. Sorry. Okay. And then 89 we compare with 29. So 29 is smaller. The second step, I will have this one, the same. And then after second step, what we have, I have this one and the 89. Okay. And now I compare 89 with 40. Okay. So 40 is smaller. So the next step, I will have 40 here. So we have 89. Okay. And 89, I compared again with 12. It's smaller, so we have 12, 89. Okay. And then 89 again with 42. So we have 42 here. Okay. And then this one with 10. So 10 is smaller. We put it, sorry, we run out of space. Okay. And again, 89 with 1. So we have, let's say, 1 here and 89 here. Okay. And finally, we have, after the first run, of course, when you write down like this, it takes you some time. Okay. So we have this number. Okay, 10 and 1. Okay. Okay. Everyone got it? For who not really know the bubble sort, the bubble sort is just like it for the first step. And then the second step, what we do, we repeat the action. Okay, we start with the first pair again. We try to swap them if needed and continue. Okay, so everyone at least run it in the piece of paper or whatever you have manually, so to make sense of the bubble sorts. Everyone, please. And of course we have the code there, but now do it manually. I will tell you something. So like when you finish, all students try to do it. Of course, if you get some problems, some trouble, you can always send me send a message there, ask me, or if you quite shy, send me a direct message if possible, if you want it, and not suggest that. Yeah, of course. Just take few interaction to make sense of that. Yeah, for sure. Because it what would try say TON square, but you see it step by step. Yep. We say really time consuming. So as the complexity, if we have 8 elements here, the number of steps you have to do is around 68 steps. Okay, thank you. So you see, if we try, that will be like okay. So one step is like we swap it, like this one I show you the remaining is the same, and this one I swap it with the remaining is the same. Okay, yeah. So the goal is just, you see, and then we can do it like, continue like this. Will be like this one, okay, and then we have this as 12 and 18. Then we have it, we swap it to 42 and 10, and you see the 10 with 18, 89, and then 1 with 89. Okay, so we have first step, first iteration, and then we do it again. Okay, so we swap 29 with 80. We can copy it, this one. Okay, that is what we have finally. So then we do the swapping again and again, no? So we have 40, okay, and we have 12 and this one, and we have 42 and this one, and we have 10 and this one. We have 1 and okay everyone, is it clear? Can you see my running? Okay, and then we have this, have it, okay, yeah. So now my question for you, in this system, so you see these algorithms, we have algorithms, but what you can see is that now we try to move this one, this go here, it's a purple socks, you see, finally here, and with this one, it's just moving to the right, okay, and of course next time we have like something better, yeah, let's say this one, 10, 40, we don't have to do anything, we have this. Now it is easier, then we have 40, and then we keep it like this. We don't need to do anything, and sometimes we need to swap, sometimes we don't. Okay, so that's it. Now if we analyze it, what we can say is each iteration, what we can have is we have always n-1 comparison after the first one. You see, we have to compare n-1 time, okay, and then we have to do from 0 to n-1 swapping. Okay, so do you agree with these two remarks? Then my question is, in which situation we have no swapping at all? For the first iteration, let's say for the first iteration, when we have no swapping. The others, So imagine what we have is this one. No, because we have to go through on pair. Okay, and I don't need to swap anything. Means that each pair are in the correct position. That will be the case when we have the array is sorted, is good king. Okay, because if there is something in the middle, of course we need to swap them. We may swap them in many times. Okay, one time or many times. But if we have zero swapping for the first iteration, it means it is sorted. Okay, we can say like that. And now for the worst scenarios, for the first iteration I have to do n-1 swapping. What happened? In which situation that we have n- swap? This is when we for the first iteration, for the first bus. That means that after we run for the first iteration through the array, I need to do n- swap. Here, after first pass, we met n- swap. That is when you have here. First, the first element here, we have here, we have to do n- swap here now for the first iteration. We have this one. This is the biggest value in the array, and we compare with swap. We compare with swap. We compare with swap. We compare with swap. Compare with swap. Compare with swap, and then swap. So we have n- swap because the first element is in the first position, and we have to swap them to move it to the last position. Okay, is it clear, everyone? Is it clear? Okay. Now, in an algorithms in general, for these algorithms, we can always do this one. For do for loop, the way we implement it is quite different from what you normally use in your basic C++ programming. Let's focus on this one. We have an out, we put it at the element -1. We do until our 1, we increase, and we do the if, and we swap. Okay. But now there's one thing I want to ask you. So you know that in this one, if we implement it, we have to do some integration. Okay. We do one iteration, and then we stop. We do it once iteration again and again. In algorithm in general, we call it. There's some properties you want to check. We call it invariant. invariant is something is correct, always correct. Okay, so we say in this case I want to ask you like what is the invariant after each pass through the array and the buffer sort. So here we do the for loop. After we finish one loop like this, what is always correct? After we compare and swap, or in other words that we say, what do we want to do after each iteration of the inner loop of the loop here? What do we want to do after finishing this loop? What do we want? Where is it? Yes. What we want is after each iteration, we want to move the biggest value to the correct position. Okay, that is what we have. And now let's say, let's try to analyze it. We say for each iteration, we will move the biggest value to the correct position. It means to the last position here. Each time we do like that. Okay. So for the second time, we move the second largest value to the second last position. Okay. So each time we do like that, we can put one number in the correct position. So if we have an array of n elements, we will do it n times. Okay. Each time we move one element to the correct position. We do it n times. We have n elements in the correct position. Then we have the sorted array. Can you get it? Okay. So we say invariant is after each iteration, we move one number, the biggest value to the corresponding position. Okay. Is it clear, everyone? Okay. Now look at the code. This is why people put it like this. So we have n elements. We will do it. The outer loop means we just try to count the number of steps we have to do. Okay. We have to do it n minus 1 time because n and we don't have to sort the last element. Okay. And then for each element, we try to put it from, you see, this keyword. It's been in the array. We try at the beginning, we try to do from the, we try to start to say, to move the biggest, the largest item to the last position. Okay, this is n minus 1. Okay, and we do a swap in the middle, we do mathing. And finally, we know that the biggest, the largest value will be here. Okay, next time, the our loop will be here. We try to find the value to move it to the second last element. Okay, our minus 1. And we do the swapping, we move everything to here. Okay, and next time we know that these two numbers are in the correct position and we don't have to check, we don't have to do anything with them anymore. Okay, and we move to this one. Okay, and our minus 1 again, so we the third last position and so forth. Okay, so you see the meaning of this code. Is it clear for you? Okay, I think that's it for this section, and that all I want to tell you. Now, this is the homework. The homework is that I want, you see that this put in backward, this is put in the forward. I want you to do this one. I want you to sort the code, use the code, modify the code at home in the homework. Okay, sort it from the left to the right to the left. Okay, it's been work with element from the right to the left. Okay, sort the array in descending order and use 2 forward loop. Okay, that will be 3 tasks for you to play with these algorithms. Okay, everyone, and that's it for today, everyone. Thank you. If you have any question, feel free to tell me. Okay. Okay, right. All right. Any other things? Any questions? Otherwise, people, that's it for today. Thank you. Try to work with the play with the homework. Okay. And next time we will have one quiz for you. Okay. Bye bye. Thank you.